Today we're going to do section 6.4, the Gram-Schmidt process. This is just a simple algorithm for producing an orthogonal or orthonormal basis for any non-zero subspace of Rn. So let's look at example 1. Let W equals span of x1 and vector x2, where x1 is 3, 6, 0 and x2 is 1, 2, 2. Construct an orthogonal basis v1 and v2 for W. Let's look at the figure below. W is with x1 and x2, and the projection of P onto x1 and x2. The component of x2 orthogonal to x1 is x2 minus vector P, which is in W because it is formed from x2 and is a multiple of x1. So keep that in mind as we go through this. So what we're going to do is we're going to let v1 equal x1. And let v2 equal x2 minus p. And x2 minus p would be x2 dot x1 all over x1 dot x1 times x1. This would equal 1, 2, 2 minus x2 dot x1 is 15, x1 dot x1 is 45, times x1, which is 3, 6, 0, which would then be 0, 0, 2. So v1 and v2 is an orthogonal set of non-zero vectors in W. Since the dimension of W is 2, the set v1 and v2 is a basis for W. Theorem 11, the Gram-Schmidt process. Given the basis x1 all the way to xp for a subspace W of Rn defined, v1 equals x1, v2 equals x2 minus x2 times v dot v1 over v1 dot v1 times v1. v3 equals x3 minus x3 dot v1 over v1 dot v1 times v1 minus x3 dot v2 over v2 dot v2 times v2, and so on and so forth. Then v1 all the way to vp is an orthogonal basis for W. In addition, span v1 to vk equals span x1 to xk for 1 is less than or equal to k, which is less than or equal to p. Orthonormal basis. Normalize or scale all of our vectors. So let's look at example 2. Find the orthonormal basis for the orthogonal basis found in example 1. So we're using what we had in example 1. So we're going to let x1 equal v1, which was 3, 6, 0. And we're going to let x2 equal v2, which was 0, 0, 2. So what we're going to do is we're going to normalize these vectors. And to do that, u1 is going to equal 1 over the length of v1 times v1. So this would be 1 over the square root of 3 squared plus 6 squared plus 0 squared. Times my vector. And this would be 3 over the square root of 45, 6 over the square root of 45, and 0. If you notice, there is a perfect square in the denominator. So this would become 1 over the square root of 45, 2 over the square root of 40, or square root of 5, sorry. And 0. And then u2 would be 1 over the length of v2 times v2. So this would be 1 over square root of 0 squared plus 0 squared plus 2 squared times 0, 0, 2. This would equal 0, 0, 2 over the square root of 4, which would be 0, 0, 1. So that's how we find our orthonormal basis for the orthogonal basis in example 1. Theorem 12, the QR factorization. If A is an m by n matrix with linearly independent columns, then A can be factored as A equals QR, where Q is an m by n matrix whose columns form an orthonormal basis for column A, and R is an n by n upper triangular invertible matrix with positive entries on its diagonal. Let's look at example 3. Find the QR factorization of A. So first, let the columns of A be x1, x2, and x3. So we're going to have this be x1, x2, and x3 when doing this problem. We need to find the orthogonal basis for column A, which equals the span of x1, x2, x3. So step 1, we would find the orthogonal basis for column A. So I want you to try to do that on your own, and you should get, we'll label those V1, V2, and V3. One, 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 one. Negative 3, 1, 1, 1. Zero, negative 2/3, 1/3, and 1/3. And we can actually scale this to get rid of the denominator and actually have 3 V3 to have 0, negative 2, 1, 1. So this is the orthogonal basis for column A, which is also equal to the span of x1, x2, x3. Step 2, we need to normalize V1, V2, V3. When we normalize them, we'll call them U1, U2, U3. So when you normalize them, U1, so I want you to try this on your own again, equals 1/2, 1/2, 1/2, 1/2. U2 would equal negative 3 over the square root of 12, 1 over the square root of 12, 1 over the square root of 12, and 1 over the square root of 12. Which then you notice that you have square root of 4 in there. Since nothing will cancel out, we can leave it if we want as just the square root of 12, since it won't cancel out with anything in the denominator. I usually only find my perfect squares is if it will cancel out with anything in the numerator. And then u3 would be 0, negative 2 square root of 6, 1 square root of 6, and 1 square root of 6 over the square root of 6, sorry. So then the columns become matrix Q. So then our columns become matrix Q. Or these vectors become the columns of matrix Q. And then from theorem 12, A equals QR. To find R, you would take Q transpose Q because it equals I, because the columns are orthonormal. So A transpose A equals Q transpose QR, which equals IR, which equals R. So the formula we would use for 3 R equals Q transpose A. So it'd have 1/2, 1/2, 1/2, 1/2, negative 3 over the square root of 12, 1 over the square root of 12, 1 over the square root of 12, 1 over the square root of 12, and 0, negative 2 over the square root of 6, 1 over the square root of 6, 1 over the square root of 6. So that's Q transpose times A, which is 1, 1, 1, 1, 0, 1, 1, 1, 0, 0, 1, 1. And you would get 2, 0, 0, 3 halves, 3 over the square root of 12, 0, and then 2 over the square root of 12, 2 over the square root of 12, 3 over the square root of 12. So this is an n by n upper triangular matrix, invertible matrix, with positive entries on its diagonal. And that is the QR factorization. So I didn't show the work in step 1, step 2, and step 3. I wanted you to try to do that on your own. So just remember for step 1, you needed to find the orthogonal basis for column A. So that's what we did in step 1. Step 2, you needed to normalize them. And then step 3, from theorem 12, we found R.